Arslan Atta.
My name is Jake McRae.
My name is Todd Parker.
And my name is Jonathan Yu.
We are Embedded Team 5, and we did an automated delivery system. We were inspired to do this project by the Amazon automated delivery robots known as Kiva. They use these robots to pick up packages in their warehouses to deliver them from where they are stored to where they are being packaged for delivery. These robots work on a system where they know exactly where their target objects are and where they need to be delivered to. Our goal with our project was to take this system and this concept and bring it down to a smaller scale and see if we could find randomly located objects and items to deliver to where they need to be.
In order to implement our system, we designed a playing field that is divided into 3 separate zones. We have the playing field zone, which is the top 3 foot by 2 foot area of the zone, and this will contain 5 blocks randomly placed of different colors, red, green, and blue. We have a sorting zone, which is 3 foot by 6 inches, where the first rover will deliver the blocks to regardless of color. And then we have 3 delivery zones that are 1 foot by 6 inches each, where the second rover will deliver the blocks to based on their respective colors. There are several different observable behaviors and elements incorporated within our system. First, we will have a simple UI to operate this system, which will be written in Qt and contain a map of the field. Rover 1's operation will traverse the playing field and pick up objects one at a time as it moves them to the sorting zone. The rover will not cut diagonally across the playing field, but only move through the X and Y axes. Upon delivering an object to this zone, it will resume its operations and scour the playing field for other objects. Once an object has been placed in the sorting zone, Rover 2 will begin. It will pick up the objects in the sorting zone and deliver it to the correctly colored delivery area in the bottom section of the play area. And every time it moves an object into the right zone, it will go back to its home base on the far left side of the sorting zone and wait for another object to be placed. The diagram on this page is an example delivery run of our system. As you can see, Rover 1, which is indicated by the black block in the playing field, moves towards the green cube, which will then be delivered to the sorting area following the path located by the arrows. After it has placed the cube in this area, it will go back and look for the red block, while Rover 2, indicated by the black block in the sorting zone, will move over to the green cube and sort it in the proper zone. In this section, we'll be giving a brief system overview. The following slides will break down the major aspects of the system as represented by our task diagram seen to the right. We will be reviewing major threads, message queues, interrupt handlers, and why we chose the specific design that we did in order to make our system and project succeed.
The sensor mapping thread controls a servo-mounted IR sensor and maps out the location of objects detected on the playing field. The grabber thread controls a servo-mounted arm that can swivel to detach objects that are picked up by the Rover 1 and Rover 2. The Rover 1 motor control thread implements an algorithm to navigate through the play area, branching to located objects and delivering them to the sorting area. Similarly, the Rover 2 motor control thread implements an algorithm to navigate the sorting area as it detects objects placed there for delivery. The encoder thread uses a combination of encoded data from the rover and directions from the motor control threads to implement the algorithms in the other threads.
The pickup thread is similar to the grabber thread, except for the fact that it uses information from the PixieCam to determine whether or not to drop the object based on color. These last 2 threads simply act as information grabbers for the pickup thread.
We decided to separate movement into the motor control and encoder threads to make for a more robust implementation. By passing the target location rather than the direction and distance to move, it allows for a better ability to adapt to new. Here we have some of our more important interrupt handlers. The sensor ISR reads the IR sensor values on rover 1 and sends them to the IR mapping thread, which keeps track of the location of all the objects on the playing field. The encoder ISR pulls timers connected to the encoder square wave approximately every 100 milliseconds. This data will be passed to the encoder thread as the most recently measured motor rotations per second, as well as transmitting a short-term average value to the encoder thread. Finally, the PixieCam UR-ISR will activate whenever the UART buffer receives data from the PixieCam and sends that data onto the PixieCam thread. Next, we will talk about how our hardware choices were made. Our first major hardware decision was on mapping sensors. We have two different setups for each rover since each one performs a different task in our system. On the first rover, we have a server-actuated IR sensor based on an algorithm developed at Sungkyung Kwan University in South Korea. Based on this algorithm, our IR sensor is rotated along a 90-degree arc by a servo, taking periodic sensor readings as it does so. By using our known rover location and the distance found to an object, we can then use the angle at which the servo is to calculate its approximate position in the actual playing field in an XY coordinate. This approach provides several advantages versus a fixed position sensor, some of which are listed here. Primarily, it allows us to cover a greater area with the sensors in a shorter amount of time to keep us from having to do multiple trips across the playing field, and it has a sweeping focus for a larger net to be cast for object location. Conversely, on the Rover 2, we have a single fixed position IR sensor. We use this because it has a simpler use case, having only to detect things in the sorting area, and so a simpler use case leads to a simpler design. This has several advantages in and of itself, such as complexity versus reliability, where the more complex something is, the less reliable it is, and the more likely something will go wrong. And a narrower focus allows for a more accurate reading along the length of the sorting area. Our second major area of hardware design choices came with the block pickup and release functionality. It consists of a hardware Hall effect sensor and a servo-mounted arm with a PixieCam and magnets. For those not familiar, a Hall effect sensor detects a changing magnetic field and therefore can detect whether or not a magnet is nearby. All of our blocks on the playing field will have a magnet on top, and we have a servo-mounted arm with a ferromagnetic material that will be attracted by the magnet and pick up the block. The PixieCam will determine the color of the block for where it needs to be placed, and the servo can move the mounted arm out of the way to disconnect from the top of the magnet on the block. The advantages of this design over something such as an electromagnet on the rover is that it's low power. It offers redundancy in the fact that we have the Hall effect sensor to always check to make sure that it's still there, and it is very simple, and as stated earlier, a simpler design is less likely to be faulty. This concludes our presentation for Team 5. If you have any questions, please leave them in the comments below, and we will be sure to try and get back to you.